Welcome, everyone. Thanks for joining us for today's webinar. My name is Jessie. I'm the content strategist here at RadiaSoft. Before we get started, I would like to remind everyone that you can submit your questions using the Q&A button at the bottom of your screen. Please do use the Q&A rather than the chat so that we can record your question and follow up later. We'll address those questions during the Q&A at the end of Kathryn's presentation. We are recording this webinar, so if you miss anything or have to leave early, don't worry. We'll send it out in a few days' time, and you can watch it on our YouTube channel. So let's go ahead and jump right in. Today's talk is Laser Amplification Simulations with Silas in Sirepo, and our presenter is Kathryn Wolfinger. Kathryn is an associate scientist with experience in laser wake field acceleration and plasma channel formation while at CU Boulder, as well as solar wind and ionospheric physics through internships with NASA Goddard. Kathryn received her BS in physics and mathematics from the University of Evansville and her MS in physics from the University of Colorado Boulder. Again, please use the Q&A button at the bottom of your screen. And Kathryn, take it away.
Hi, I'm Kathryn Wolfinger, an associate scientist at RadiaSoft, and today I'll be talking to you about laser amplification simulations using the Silas software. I'll break it up into 3 parts. First, we're going to talk about some of the components of Silas, and we're going to benchmark it against experimental data before moving over to Sirepo and experimenting with the GUI. So as I said, Silas is for simulating crystal CPA amplifiers. The figure you see here is an example laser amplifier layout provided by Berkeley Labs Bella Center. In it, you can see 4 amplifiers in those blue boxes, each with a crystal in the center and a set of mirrors on the edges. It's a bit confusing at first glance, so I have a basic amplifier layout at the bottom of the page, showing the laser coming in to each set of a crystal and several mirrors, passing through that crystal n number of times before moving on to the next amplifier, eventually leaving the system. In between those amplifiers, you can have telescopes, lenses, beam splitters, all dependent on how you want to manipulate this laser pulse. Some of the main difficulties we faced with the software were efficiencies, so how to efficiently propagate the laser fields, how to efficiently calculate gain when we have 3D crystals and 3D lasers. So let's talk about that first one next, the gain calculation. The answer to the problem is slicing up the laser and crystal. So the laser slices are SRW compatible for those who use that software. And the essential component are 2D arrays of the fields and the photon count. The laser is capable of propagating in either direction through a crystal, which enables those multiple passes in each amplifier. On the right, I have an image of the intensity at the top of the page, an example from the simulation after 10 passes through an amplification system, and you can see how the profile of that beam, which was originally Gaussian, has become more flat-topped. The crystal is likewise sliced up. That's the center image you see there, the long crystal cylinder, where the yellow at the center is higher temperatures, purple is lower on the edges, and we cut that up into evenly spaced slices. The fewer slices you have, the more efficiently the simulation will run. The more slices you have, the more accurate your results. So it's about striking a balance between those two. But generally, a relatively low number of laser and crystal slices is sufficient. The crystal parameters are achieved primarily through Phoenix simulations of 3D thermal transport. You're seeing the output of one of those simulations in that purple and yellow crystal cylinder. Its primary data is stored as a 2D array of excited state densities. And now that we have these slices, when we go to calculate the gain, instead of a 3D calculation, we essentially have a 2D mesh, and we can just apply the 1D Franz-Nordvik equation to each cell. This is done for the full crystal and laser by stepping through the crystal slices, and at each crystal slice, propagating through every one of the laser slices. As this is done, the local excited state density is updated so that the same crystal can be used for multiple passes. And the final figure on this page on the right is an example of that excited state density. And you can see this is after 3 passes through an amplifier. 3 passes of a laser through the crystal being shown here. And from the depletion of those excited states, you can see the results of the gain. Propagation of the laser is achieved through Fourier optics and operator splitting. Linear thermal lensing is also included. So the heat on the temperature of the crystal is going to affect the propagation of the laser, and we will get focusing of the laser from that behavior. Such effects become more important at higher repetition rates, at higher pump repetition rates, where the temperature of the crystal increases. Chromatic effects are not yet included. Another important piece of laser modeling is the wavelength, getting that behavior right. There's both the chirp, which is the variation in wavelength from the stretching or compressing of the pulse, and the bandwidth, which is an inherent variation. So the figure on the right is an example of how we're implementing the chirp. So the x-axis is the pulse slice. You can see for the first pulse slice, we have around 880 nanometer wavelength, and at the end, it's around 730. The laser slices, which we discussed before, are each given a single wavelength. That variation can be shown on the figure on the right here, from the front of the pulse at slice 1 to the back of the pulse at slice 5. The bandwidth is achieved by, at each of these locations, adding additional slices, and with wavelengths that vary around that central value. This allows us to replicate, experimentally see in redshifting quite well. I'll show you later on. But first, let's stop at the crystal and give you a few more details about what manipulations are available here. The crystals can be varied in dimension, absorption length, initial temperature. The pump pulse can be varied in pulse direction. So you can pump this pulse from the left, the right, or both sides. The energy, the waste, the profile, and the rep rate. So we support both 1 Hertz and 1 kilohertz rep rates. The simulations, there are those 3D Phoenix. There are those 3D Phoenix thermal simulations, and then there are also approximate analytical models for when a quicker answer is desired. So this results in some very lovely visualization. So the figure on the left is showing a temperature profile of a crystal, and you can see it was pumped on both sides with the higher temperatures there and a drop off towards the middle, as well as very low temperatures outside of the waist of the pump pulse. And we also allow you to look at those 3D models of the crystal and move within the crystal and see how those temperatures are varying against the initial. With all these tools, how do we replicate experimental results? Well, we were once again provided with some data from the Bella Labs. This is for their 100 terawatt amplifier. It's a system of 3 crystals, 10 gain passes total. There's a beam splitter in there, and the crystals are pumped with super Gaussian pulses. The first thing I want to discuss is the amplification. On the right side, we got great agreement. You can see it goes from under 10 millijoules as the input to the system before passing through the 3 amplifiers and coming out at over 1 joule, with very little variation between simulation and experiment. We also achieved comparable redshifting and bandwidth. So the figure on the left shows the redshifting versus amplification over the course of the full system. The dashed lines are experimental results, the solid lines are simulated results, and then the colors correspond to the position in the system. So green is the laser pulse that's going into the system, black, red, and blue are after each of the amplifiers, and so blue would be the final output of the full system. As you can see, the bandwidth spread is similar, although we do slightly overestimate in simulation that redshifting. And the total variation from about 800 nanometers to around 810 nanometers is achieved. These are excellent results, but let's stop looking at plots and let's stop looking at plots and slides and go look at the GUI itself. So for the user, how can you interact with Silas? The underlying physics engine is an open source Python library for those who are interested. And then there is the intuitive GUI online that I'm about to show you. And we'll be modeling the exact experimental setup that we were just discussing. All right, so we've made the switch over to Sirepo, and we're going to pull up Silas out of the supported codes. Go to our examples and open up the 10 terawatt amplifier. So here is what any Silas example looks like. The top right, you have 3 tabs: the laser pulse, the amplifier, and thermal transport. Laser pulse is where you set the parameters of the pulse you're going to be sending into your system. So we allow you to control energy parameters, transverse and longitudinal parameters, including the chirp, which is calculated here based on your full width half max parameters. And as an output, you can look at your laser pulse, you can look at the intensity, the phase. We have a lot of options up here, including variation longitudinally and looking at slice instead of the total summed result. If we go to wavelength and save those changes, we can see that redshifting plot that I had on the slides earlier. And if we were to vary either of these parameters here, we would be able to vary this slope here. Okay, so now that we have our laser implemented, let's go over to the amplifier. Now, let's restart that. System allows you to select the options you want and drag them down into the beamline. But this beamline is prepared for us. We have AMP2, AMP3, and then AMP4. There's a beam splitter in the middle and 2 telescopes. So for each of these elements, the position at the top is where in the beamline this exists, so the drift length essentially since the last element. And you can manipulate and adjust each of these as you'd like. So if we open up a crystal, we can set a lot of the geometry parameters that we discussed before. We can set how we're going to propagate that, as well as the initial temperature. We can set all the pump pulse parameters. What order do we want? High order Gaussian or a top hat? Are we going to pump from the left, the right, or both sides? And then we will show you a very quick plot of the N0, N2 parameters, which will influence your thermal lensing. And you can set those parameters for each of your crystals. By replicating the same crystal here, we allow the excited state densities to be updated during the simulation. And so as you can also update the mirrors. These watch points allow you to check the laser at that point. Here's the splitters, and the telescopes allow you to set all the important parameters necessary. As the simulation runs, you'll get the plots out before the end result, allowing you to play around with them. Something's not looking how you want, and you can go back and make changes. So here's that initial laser pulse we were looking at before. Now, while this simulation is running, why don't we go over and look at the last tab on Silas, which is thermal transport. So this tab is quite useful. You can come here. You can select any of the crystals that you have implemented on the previous tab. You can make changes to them and see how that changes their parameters. If you like those changes, you can save them and they'll be implemented on the previous tab. Or if you don't like your changes, you can revert back to what they were originally. Here's the parameters for the crystal that we can change. Here are the parameters for the pump pulse that we can change, and then a few simulation settings. And so this one already ran. Again, here's that radial temperature profile. On the right here, here's the radial and axial profile that I showed you before. Here is that interactive crystal mesh that allows you to play with it. We can vary where we're cutting it off, and so we can look at different positions, and we can see that this is pumped from both sides as the temperature is increasing again. When we get back to the far end, it gets fairly low in the middle. So these are all available to let you fine-tune your crystal without running through multiple full amplifier simulations. Now let's go back and look at the results of that beamline. As you can see, here's our initial laser pulse. And then here's the amplifier, the crystal. After the first pass, you can see there's a slight depletion of excited states. There are other options here. You can look at the longitudinal distribution of excited states. So we can see that it's that dual pumped structure that we'd expect, but the laser pulse has depleted more at the end because it's been amplified during its procession through the crystal. Here's that second pass, more depletion. Third pass, even more. And then down here is after the fourth pass, it's essentially depleted the crystal completely within the waist of the laser. At this point, you can see that the laser pulse itself has become quite focused by those thermal lensing effects that we discussed before. And so we split it, and then after this, we have to pass it through a telescope. This is some of the capabilities of the Silas app: full control over your beamline, your laser pulse, and the crystal itself. I hope you found this helpful, and thank you very much.
Thanks, Kathryn, for that excellent presentation. We've got a couple of questions lined up for you in the Q&A. I'll go ahead and throw those to you. The first question is, you mentioned titanium sapphire crystals as your gain medium. Are there other crystal types or gain mediums available?
That's a great question. Thank you for that. As I said, we use titanium sapphire. That is the system that we were modeling against. At this time, that's the only available gain medium. However, implementing new materials based on demand or request is quite possible. If there's something you're interested in, please reach out and let me know.
Thank you. Next question up is, you had mentioned support for pump pulses involves different repetition rates. Does that mean you support the full range from 1 Hertz to 1 kilohertz?
That's also a good question. This is a little more of a tricky area. So pumping at 1 kilohertz is more of a recent implementation, and it results in the crystal temperature, increasing. And so you can reach a steady state at 1 kilohertz, but in between the range of 1 hertz and 1 kilohertz, it's a little less well defined. So we do support some frequencies within that range, but not the full range itself.
All right, great, thank you. That's all we have time for today. Thanks for joining our RadiaSoft webinar series. We'll send you an email shortly with a follow-up link when we post this to YouTube. And a happy holidays to everyone who celebrates.